Biostat 6611, skills for the rest of your life, bootstraps and probability. It's the bread and butter, baby, what's your jam?
Good day, Bio 6611. In this lecture, we're going to look at how we can derive, for simple linear regression, the variance of the beta coefficients that we derived in the previous lecture. We'll start with a review of some important and useful formulas and sort of what we're working to solve for. We'll then work on deriving and calculating those variances, and we'll end with just a quick summary of how we can also similarly derive the standard error of the mean for calculating things like the confidence interval. So let's start with some formula refreshers. Just to sort of highlight again what we had from last lecture, we showed at the top here that we can solve for beta 1 hat and beta naught hat by taking that first order partial derivative, setting equal to 0, and then solving for our respective quantity. What we're going to focus on in this lecture set instead is on the below equations here, our standard errors for the beta coefficients. We'll see how we can apply some formulas and properties of the variance and random variables to get to these representations. On this slide, we see a slew of helpful properties and formulas to refresh ourselves on, or introduce for the first time, depending on our backgrounds. The first thing we can know, we previously introduced on our first line here, that the variance of y, we can solve it with some of the formulas we had before, but if we happen to know the expected value of our random variable y squared, and also the expected value of y itself, we can use those to calculate the variance. However, in some cases, we may be interested in other quantities within that equation. For example, we may have some situations like we'll see ahead, where we need to know the expected value of y squared, but what we really only know is the variance and the expected value of y itself. On the next chunk of our formulas here, we see the property of a constant c times our random variable y, where for the variance, if we pull that out, we actually square the term, and for the standard error, we take the absolute value. In both cases, in case c was negative, we preserve that the fact the variance has to be positive, greater than 0. We then see a slightly more complex representation here where we have 4 constants and 2 random variables for our covariance. So if a, b, c, and d are all constant values, and x and y are our 2 random variables, the covariance of a times the random variable x plus b and c times the random variable y plus d will be equal to those constants a times c multiplied by just the covariance of x and y. Well, we can note what this says then is that the d and the b constants that we have in our equation, what they're really doing, if we think about actually picturing something maybe in our mind like a normal distribution, it's shifting the location. So it might be saying, whatever mu is, I want to add 10 to it. And so while the distribution itself is moving, it's not going to affect our covariance. And the scale that we're looking at with things like a and c actually multiplying directly to our random variables. We then see here that we have, for our variances, the properties of trying to add or subtract 2 random variables, and we can generalize this to the case where we have multiple random variables as well. But generally speaking, we'll add the 2 variance terms together, and the only sign that will be affected here is the plus or minus, depending on if we're x plus y-ing or x minus y-ing our 2 random variables. Then just some refreshers as well. We do have those formulas that we could use to calculate the variance and the covariance if we had the original data. And we also below here see an equation for the correlation coefficient for that Pearson's linear correlation, which as well may be useful just to note and keep in mind. So with that, let's move to calculating the variances. Now, before we start by deriving the variance of beta hat 1, we're going to do a little rearranging of our beta hat 1 term. It turns out, with our representations in algebra, we can do a lot of tricky things to show it in different but equivalent ways, which may be more or less advantageous for things like actually plugging in values to solve for an estimate, or something like this where we might want to work with a form that's easier to actually apply the properties we know and reviewed on the previous slides. So essentially here we'll start with what we had for our equation for the beta hat 1 that's useful for solving with our 5 summary statistics. But we can note then if we actually multiply out our xi minus x bar term to each of our y minus y bar terms, we can get to a point on our next equation here where we see that we've separated them out, and with some simplification we get to a representation below here where we really have each observation y times that person's predicted value x minus its mean, all divided by the sum of all of our xi's minus x bars squared. And this will just be useful to help us more easily derive the variance on the following slide. We can also note as well that I've just provided a note below at the very bottom here that briefly shows us how we can state the fact that y bar times the sum of the individual observations minus x bar equals 0, so that that term up above here in our equation can sort of be taken out of consideration to make things easier to work with. The one thing I'll just highlight that I think is again a useful trick is our multiplying something by an object over itself, or n over n, which is essentially 1. So you don't have to do any other manipulation to the rest of the equation, but it does then allow us to show that we have n times the sample mean minus n times the sample mean, which is 0. Okay, so with all of that out of the way, we're finally ready to derive the variance for our slope and walk through step by step how we're doing it and those properties that we're applying. And so we see here, to get us a jump start, we're going to calculate the variance of beta hat 1, or we'll rewrite that in terms of what we just simplified or derived, rearranged on our previous slide. And so with that, let's pause and cut over to the whiteboard to work on it by hand, step by step. Okay, we've switched over to our whiteboard, and we have a few things we can note based on our assumptions of regression that we'll see come into play here. The first thing is that we assume our errors are independent in our model. In other words, what that helps us to state is that really each one of our outcomes based on our simple linear regression model are independent of one another. One way we can note this mathematically is that yi is independent of yj with this sort of upside down T shape. Specifically for regression, for our second point here, we are working with that assumption of the expected value of y given x, so given our predictors. Because of this, we can treat our x as fixed or known quantities. They're not themselves random variables, but just constant values. Further, because we assume that yi and yj, our outcomes, are independent of one another, that would imply that the covariance of yi and yj are equal to 0 for all combinations of I and j that aren't equal to each other. In other words, the covariance of yi and yi is really just the variance of yi. For the homoscedasticity assumption we make in our regression modeling here for the ordinary least squares, what this implies then is that the variance of y1 is equal to the variance of y2, which is equal to the variance of our nth observation yn, which just means that we have that estimate of our MSE, or that sigma squared y given x. And so we'll use these facts to help us in the process of applying the properties we saw in the previous slide, and to note why some of these things can be done. Okay, now let's work on actually walking through the steps and applying some of those properties and formulas we saw previously to see how we can derive the variance of beta hat 1, which we see we've written on our whiteboard what we had on our previous slides. The first thing that we might want to do is to take advantage in our first step of that property of the variance of cy being equal to c squared times the variance of y, where c is some constant value. And specifically here what we can note is in our denominator there, we have the sum of xi minus x bar squared, which is a constant because, again, thinking back to our second point up above, if we just briefly note we have 1, 2, 3, and 4, that second assumption then is treating those x's as a known constant. And so what we can do is we can write out in our numerator the variance of x1 minus x bar times y1 plus dot dot dot, everything in between, up to xn minus x bar, yn. And now because we're pulling out that constant term of the sum of our xi minus x bar squared, in our denominator we can note that we still have that sum of xi equals, from I equals 1 up to n, our sample size, xi minus x bar squared, but really just the whole term itself is squared. From this point on, the next thing that might be useful to do then is to actually distribute our variance out to each of the separate terms. So in our focusing more on our numerator now, making it sort of explicit that we have the variance for each one of these xi minus x bar times yi terms. And so in the next step we will distribute our variance, and so here we see that we will rewrite that here as the variance of x1 minus x bar y1 plus dot 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 plus the variance of xn minus x bar yn. Now the one thing we might need to make note of here is the fact that we have, if we note our, just right up here, the variance of x plus y is really equal to that variance of x plus the variance of y plus 2 times the covariance of xy. So what we actually have right here, even though we've distributed that variance out for our first part of our terms here, is that we still need to add then all of these combinations of 2 times the covariance of xy. Or in our case, y1 and y2, y1 and y3, y1 and y4, all the way up to y1 and yn, basically all of our possible combinations, then starting again at y2 and y3, y2 and y4, and so on. And so what we see here is that we can just write this out initially just to get an idea of what we're working with, as our first term here being, let's see, 2 times x1 minus x bar times then our second observation x2 minus x bar times then the covariance of y1, y2, and we're going to lose a little space here, so I'm going to briefly zoom us out here to get a little more room to work with. What we can note again is that that pattern just repeats itself over and over, all the way up to 2 times xn minus 1 minus x bar, xn minus x bar. Zooming out just a little more for this wicked long equation, times the covariance of yn minus 1 yn, which may have gotten a little bit cut off there, but hopefully is mostly on the screen. And then we'll close our little parenthesis there. All of this then is still divided by our sum of I equals 1 to n, xi minus x bar squared, all of that squared. So again, what we can do now is we can note that actually, because of that assumption of independence from point 1 above, which implies point 3, the independence is that the covariance between any of our two y's is 0. What we know is that this goes to 0, everything in our little dot 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 goes to 0. So really, this really long chunky part out here all goes to 0. And so what we're left with actually then is slightly simpler to work with. The variance of x1 minus x bar y1 plus dot dot dot, the variance of xn minus x bar yn, again all divided by the sum of our xi minus x bar squared, all squared. So at this point then we can maybe zoom back in a little bit here, since we don't need as much space anymore, and scroll down just a little bit. And what we can work with now is actually applying the other properties we noted here based on the fact that x1 minus x bar, or any x minus the mean, is really a constant term. And so what we can rewrite this as is x1 minus x bar squared times the variance of y1 plus this applied to all of our observations until we get up to our nth one, xn minus x bar squared, the variance of yn, again divided by that summation we had before, xi minus x bar squared, squared. And then the last step we can do here is apply the fact that we know the variance of yn is going to be equal to that sigma squared y given x, or actually the variance of any of our y's will be equal to that same term because of the assumption of homoscedasticity of our variances. So we just scroll down a little more to get a little more room. What we see here then is that we have x1 minus x bar squared, sigma squared y given x, plus dot dot dot, the same thing over and over again, just with our different subscripts, up to xn minus x bar squared times sigma squared y given x. And then just keep carrying through with our denominator here, unchanged. And the final step we can note is that what we really have then is this one term, sigma squared y given x, repeatedly, so it may be helpful just to simplify this instead of having to write the dot dot dots continuously, is to say we have sigma squared y given x times the sum of I equals 1 to n xi minus x bar squared, all divided by xi minus x bar squared squared. What we can note here now, what we actually have is that we have our sum of xi minus x bar squared, but we also have that right down here as well, but it's squared. So we can do slight more simplification where we can cancel out this one and cancel out that squared term there. So what we're really left with is sigma squared y over x divided by the sum of our xi minus x bar squared. Or the way we can also write it is sigma squared y given x over the sums of our cross product of our x's there. And so with that, we've simplified our variance of beta hat 1 and gotten it to that point that we can use to apply sort of our formulas or summary statistics to calculate what we find in our regression table. And so we'll pause here for a second and switch back over to look at how we can derive the variance of beta hat naught. Okay, so here we are, ready to derive now the variance for our intercept. Unfortunately, it'll be a little less unruly, partially because we're going to work with that idea that we can rewrite the variance of beta naught hat by plugging in that regression equation that we have to solve for beta naught hat and rearranging the terms for y bar minus beta hat 1 times x bar. So let's again cut over to the whiteboard to work through some of this math and see how we can get to that solution for the variance of our beta naught hat. Okay, so now I've cut over to the whiteboard here, and we can work through the calculation of that variance of beta naught hat, which we've plugged in our summary form representation for the calculation. The first thing we can note here is that we can apply that equation we saw earlier for the variance of x minus y, where in that case we're assuming just x and y are two arbitrary random variables, is really going to be equal to the variance of x plus the variance of y minus 2 times the covariance of x and y. And so we can apply this general idea first, and then further tease out and apply other properties to see how it comes into play. So what we can see here is that if we rewrite our variance equation here, we have the variance of y bar plus the variance of beta 1 hat x bar minus 2 times the covariance of y bar beta hat 1 x bar. What we're going to note right now, just for the sake of simplicity, is that the covariance of y bar beta hat 1 x1 is equal to 0. And we'll show that in a few minutes and walk through the derivation of that proof. But what that will do then is it'll simplify that term because we don't need to worry about the covariance, and we can focus on reworking our two equations here. And so the first thing that might be useful is to rewrite the variance of y bar as the sum of our yi's over n. And then in the case of the variance of beta hat 1 x bar, we can note that x bar is a constant, so we can factor that out there and square it. And then what we have here is x bar squared times the variance of beta hat 1, which we just solved for on our previous slide. What we can then note as well is that we can treat the term here, our over n here, as a constant. We can factor that out, so we have 1 over n squared times the variance of the sums of our yi's plus x bar squared variance of beta hat 1. The next thing we can do actually to make it a little simpler and easier to work with is again noting that our outcomes or our observations are independent. We can then make a slight tweak here where we pull the summation out, instead of the variance of the sums of the yi's, we have the sums of the variances of the yi's. Where again we have I equals 1 up to n, and then plus x bar squared, variance of beta hat 1. The next step we can then do is apply the fact that we know that the variance of each one of our yi's is equal to that sigma squared y over x. And so here we can then apply that to say 1 over n squared of n times sigma squared y over x, because we really have n of our estimates of sigma squared y given x. Then we can say plus x bar squared, and now we can just plug in that variance of beta hat 1 we had in the previous slide, sigma squared y over x, divided by the sum I equals 1 to n of our xi minus x bar squared. At this point we can note a few things here. One is that we have an n and n squared, so we can simplify that by canceling that 1n and taking our 1 over n squared to be 1 over n. The other thing we can note as well is that we have a sigma squared y given x in both parts of our equation. So we might want to pull that out to make it a little simpler. And so let's pull our equation, our whiteboard down a little bit to give a little more room. What we see here then is if we factor that out, sigma squared y given x, what we have is 1 over n plus x bar squared over the sum I equals 1 to n of our xi minus x bar squared, which arrives us at that representation of the estimate of our variance of beta naught hat. And so with that, we'll pause here, flip over back to the slides briefly to introduce our covariance of y bar and beta hat 1 x bar to show them that it's equal to 0. Okay, now we're ready to show here that the covariance of y bar and beta hat 1 x bar are equal to 0. Again, we'll make note of a few facts. For example, the expected value of yi times yj, because we assume they're independent in our simple linear regression framework, is just equal to the expected value of yi times the expected value of yj, so we can separate those out. Similarly, we can also note that the sum of our xi minus x bar, when we sum up all of our observations that go into calculating that sample mean x bar, that will be equal to 0. We're going to take advantage again of our rewriting of beta hat 1 as we did previously, and then we're going to use that to help show that the covariance of y bar and beta hat 1 x bar is in fact equal to 0, which will take a quick pause to pop over to the whiteboard to show. Okay, now we have the whiteboard ready to go to walk through the steps and some of the properties to apply to actually show that this covariance is in fact equal to 0. A few useful things we're going to do first is note that we have a lot of terms right now in this representation of the covariance that are constants. For example, we have over n divided by the sum of our xi minus x bar squared, and even this x bar here. And so what we're going to apply is that note we saw before that the covariance of something like ax by is equal to ab covariance xy. So we'll rewrite this just to get those terms out of the way to work with the meat of the problem. And so what we'll see here is that we'll really have x bar divided by n times the sum of xi minus x bar squared times then the covariance of the sums of our yi and the sums of our xi minus x bar times yi. Now, one of the things we're going to note moving forward is that this term here is just a constant nuisance parameter. And so we're just going to represent that here from here on out just by a lowercase c. That way we don't have to keep rewriting it over and over again. The first thing we can also note then as well, in going on to the next step here, is that the covariance of something like x and y can be represented in the forms of our expectations. So, for example, this can be shown to be equal to the expectation of x times y minus the expectation of x. We'll zoom out here a little bit more to get some room here on the screen, times the expectation of y. Maybe we'll just zoom in a little bit more to get it fitting nicely in the frame here. And so we're going to apply this to our next step here, where we're going to see that what we're going to have is the expectation of x times y, or in our case, what we can think of as this is our x, and this term here is our y based on that equation. So we have the expectation of the sums of our yi times the sums of our xi minus x bar, yi, minus the expectation of just the sums of our yi times the expectation of the sums of our xi minus x bar, yi. I'll just quickly tweak that to make it a little more y-ish. Okay. And so from this step on, we're going to have to do a little bit of tricky mathematical work to apply some of these ideas. And we're going to try to do them in sort of single steps, multiple things at once. So we'll break down each piece, what we're thinking about and what rules we're applying. So again, we start our next line. We have that constant c there, our nuisance set of terms. What we're first going to do is we're going to do the actual product of our yi times that xi minus x bar yi. The difficult thing here, obviously, is that they're both the summation, and these are from I equals 1 to n. And so what we can do, though, to represent this product of these two things is write it as so. So we have the expectation of the sum of I equals 1 to n of, we'll say, xi minus x bar times yi squared plus the sum where I is not equal to j of xi minus x bar yi times, we'll say yj here, just to keep our two different y's actually straight in this case. And so it's a little tricky, but that's the rule, what we're going to do to help work with this a little more. For the next part here, we're going to rewrite the expected value of the sums of our yi's. We're going to cut to the chase there and write n times mu, because we know it's the sum of independent yi's, so we're just really adding up mu n times. We're then going to, in our term here, do a little more work to get in a format that we can actually work with to see that the sum of xi minus x bar are these constant terms, and we have the expectation, though, of our yi's here. And so what we can see here is that we can rewrite this as the sum of our xi minus x bar of the expectation of yi here. And we'll zoom out slightly here just to get it all on the screen here. And add our square bracket to close it off. So now we have a pretty gnarly looking thing still, and so we'll just keep working away on it, seeing how else we can make it look a little simpler and easier to work with. And so the first thing we might want to do in the next line with our first term here is we might want to distribute that expectation to the fact that we have our two different components that we're working with. And so the first thing we can note for this first term is that we really have the expectation of the sum of our I equals 1 to n xi minus x bar yi squared plus the expectation of the sums of I equals not equal to j xi minus x bar yi yj minus n times mu. That term's kind of done and we're finished working with that. And then here we can note that what we have here is going to be the sum of our xi minus x bar times mu, because we can take the fact that we know the expectation of yi will be equal to mu. Then in our next line of code, we can apply some further properties here, our next line of our equation, not code. And we see here we then have the, not the expectation yet, we want to actually factor out that constant term xi minus x bar here. And then we will have the expectation of yi squared left over, because again, noting that our x's are treated as these constant values. Likewise, here in the next piece of our equation we're working with, we can factor out the sum of our I not equal to j, xi minus x bar there, and have the expectation of the product of, then we get minus n times mu, and we can note that we can actually factor out that mu here. So we have n times mu squared times the sum of our xi minus x bar. And the thing we can do as well is we can just note for completeness that these other summations we haven't marked are I equals 1 to n. So we're going to scroll down here a little bit to give us some more room to work with. What we can now do is further manipulate our equations. We have the sum of xi minus x bar, and we can note with here is that we have the variance of our yi plus the expected value of yi squared, based on that property we discussed earlier. We can also note that in our next step here for I not equal to j, we have xi minus x bar, and because our y's are independent, we can make it the product of our two terms there, and then just write our n mu squared sum of xi minus x bar. Now we can apply some of these things that we also know. For example, we can note that the variance of yi is equal to that sigma squared y given x. Our expected value of yi squared will just be equal to mu squared there. And each of our terms here then will just be equal to mu themselves as well for the expected value of yi and the expected value of yj. And so what we have then, if we plug those in, is the sum of xi minus x bar times sigma squared y given x plus mu squared plus the sum of xi minus x bar times mu squared minus n times mu squared sum of xi minus x bar. So at this point, it seems like we might still be a pretty far ways off from our end goal. But fortunately, we can go back to that fact that we know that the sums of our xi minus x bars will be equal to 0 when it's over I equals 1 to n. And so what we can note here now is that because everything has been put in terms of known entities like mu or sigma squared y given x, all we have left are constants in our equation. So what this tells us then is that this goes to 0, this goes to 0, and this goes to 0 as well. Or in other words, we have our constant c times 0 plus 0 plus 0. So fortunately, what we've just shown actually by getting to this point at the very end here is that it's all equal to 0. And so that is our derivation and proof that the covariance of y bar and beta hat 1 x bar is equal to 0 for our calculation of the variance of beta naught. So let's take a second and flip back over to our slides to wrap up this lecture. Okay, so to wrap it all up, we're going to look at the standard error of the mean. But to save us the headache of having to do all those derivations by hand again, we're just going to walk through some of the high-level calculations and properties here on the slide that you can think about, and we can discuss more in detail if you'd like. But remember, what we have here is that we have our predicted mean for y given some value of x, x naught. And so we plug those values into our fitted regression line, and what we essentially end up with is something that looks like this: y bar plus beta hat 1 times x naught minus x bar. We then will plug that in to calculate our variance, and we'll basically just apply those rules we saw before, treating our x's as constant, using the variance we already applied, or calculated for beta hat 1, and also noting what we just proved for the covariance of y bar and beta hat 1. And walking through those steps will get us to that equation down below here that we can use in the calculation of a confidence interval, or with that slight modification for the prediction interval as well. And so with that, that will wrap up our discussion of the simple linear regression derivations of the variance calculations for the coefficients and also the standard error of the mean estimate.